We'll start with a sketch of this problem here. So that is step 1. We have an inclined plane. We have a box sitting on an inclined plane. We are given the mass and we're given the angle of the incline. We have a force being applied horizontally onto the box. So we have maybe a person just applying a force, kind of resisting the sliding motion down the inclined plane. It's frictionless. So the next step is the free body diagram, FBD. If we draw the box, we have a contact point between the box and the surface. So we will have a normal force. We also have force of gravity, which is a field interaction. As long as this is a uniform object, it will act in the center. And then we have this horizontal pushing force. So those are the 3 interactions we have on the box. In order to apply Newton's second law, analytically, we need to split them into components. So the next step is our reference frame. So I'm going to make this sketch again. And I'm going to say a snapshot equals 0. That's not important for this problem here, but it's just a habit I have when we have problems where we are dealing with finding positions, for example. So here is my choice of reference frame. Of course, you can choose any reference frame that is an inertial reference frame, and you should get an answer that is correct according to your reference frame. Okay. So step 4 is to now break these forces into components according to our reference frame. So let's start with the X components. We have let's take the normal force. It might be convenient to maybe make a little sketch of the forces here on the side. So here's the normal force. And then I'm gonna say, well, the y coordinate is along or parallel to the normal force, and the x is perpendicular to it. So the x component of the normal force is 0. We can do the same thing for the force of gravity. So here is force of gravity. I'm gonna draw just a dashed line indicating the y directions, and one with the x directions, for example. We can recognize this is the angle theta. We're going to break into component along x, so that's the one we have right here. That's opposite of the angle, so that's a sine component. So the force of gravity in the x direction is going to be the force of gravity, or the hypotenuse, times sine of the angle theta. I'm going to now use that the force of gravity is also given in equation form as mass times the acceleration of gravity. And then we have sine theta. Similarly, now for the pushing force, can we make these dashed lines here? You can recognize this. Here's the angle 30 degrees. So the angle theta, I think it's 30 degrees in the problem. But let's be consistent, just call it theta. So this is the angle theta. We are projecting onto the x-axis, so here's the right angle. We now recognize that the x component is the adjacent side, but the vector component is going to be opposite direction of the positive x. So our pushing force in the x is going to be negative. The pushing force and cosine the angle theta. We can now go to the y coordinate or y projection. Now the normal force is all along the y direction, so that's simply the normal force, and it's in the positive direction. Put positive on that component. You should put a positive on the force of gravity up here as well. Okay. Now the force of gravity, we had a sine component x, so our y component is going to be a cosine. It's the adjacent side right here, and we see that the component is in the negative direction. So the force of gravity, y component, is negative mg cosine theta. The pushing force, we're looking for the component sitting right here, and it's downwards in the y direction. So we have a pushing force that is negative and it's a sine component. Okay, so now we've broken all our forces into components. So actually, I should say this is plus step 5 because I did include the helpful equation for the force of gravity. Step 6 is to then write Newton's second law in the components, or in component form. So we have force of all the forces in x is mass times the acceleration in x. We can sum up all the forces we have 0, and then we have plus mass times the acceleration of gravity times sine the angle theta minus the pushing force cosine theta is mass times the acceleration in x. Do the same thing for the y direction. We have them right here, so that is the normal force as a positive contribution minus the contribution due to the force of gravity and minus the contribution due to the pushing force as mass times the acceleration in y direction. Okay, so let's see how many we have. We have unknowns. We have the pushing force is given, mass is given, acceleration of gravity is 9.81, the angle is given, we don't know the acceleration. So in principle, if you're just looking for the acceleration, this equation here is all we need. We have all the information and we can solve for the acceleration. Okay. If we're also interested in finding the normal force, then we can look at this equation here. Now, keep in mind we have one equation up here with one unknown, which is good. Here we have a normal force unknown, but we also have the acceleration in the y direction, which is unknown in principle. This is where we now have to employ the 7th step, the equation of constraint. So we have 2 equations with 3 unknowns. However, we know based on the constraint motion is that the box is constrained to move on the surface. And that means that no matter where we are along that surface, the y coordinate must be equal to 0. That also implies that there's no change in y. So y, or delta y is equal to 0. And that implies that there's no motion, or no change in motion. I should not say no motion, but there's no change in motion for sure in the y direction. And that means the acceleration is 0. Okay, so now we can, let's repeat the first question we had. First question, I say equation, probably sound like question. That's why I use avatar sometimes. Avatar don't goof up all the damn words. Okay, so that's just the first equation. If we only need the acceleration, that is sufficient. If we do want to know the normal force as well, we need to include the second equation and the equation of constraint. So let's that's one equation. And the second equation is that the normal force minus the contribution due to the force of gravity minus the pushing force contribution is equal to 0 because that acceleration in the y direction is 0. This is now 2 equations with 2 unknowns, and we can solve those using our favorite tools.